Hello and welcome to Pharma-info with Shubhashish. Now today's topic is synthesis of methotrexate. Now methotrexate, structurally how it looks, first let's see that how it looks structurally, and then we'll move on to the IUPAC and subsequently the synthesis. And in between we'll just see that in which pharmacological category it belongs. Of course, it is well known to us because methotrexate is not a novel drug. It's no new to us, right? So now methotrexate, how it looks. If we just see the structure of methotrexate, you can find a strong resemblance with the folic acid, right? So now let's see that how it looks. Methotrexate is the one in which you can find one nucleus called pteridine. Pteridine, right? Okay. And it's a combination of three essential fragments, what we can say. The first one is your pteridine, the fused heterocycle with 4 nitrogen, right? The fused heterocycle with 4 nitrogen. The second one is the derivatized PABA. PABA, we all know about PABA. PABA is para-amino benzoic acid. Of course, you won't find the carboxylic at the same time amino remain as amino as well as carboxylic. Okay, there is a modification of this, and that is why I have written the term called derivatized, right? And followed by a glutamic acid. So glutamic acid, we all know that glutamic acid is an acidic amino acid having 2 carboxylic group in it, right? Chalo. And if we just merge them in a proper way, you can find the structure of methotrexate, right? Okay. Now let's see that how the structure looks. Okay. Now, so as I said, pteridine. So pteridine is nothing but it is having a pyrimidine nucleus in it, and to that pyrimidine we'll just fuse. Okay, we are going to fuse a pyrazine to it, right? Okay, so this is basically the backbone of pteridine, right? And to that pteridine, I need to incorporate what? I need to merge what? The derivatized PABA. Now, in between that derivatized PABA and pteridine, we have a methylene, right? Methylene, and it is playing a crucial role. Okay, of course, in this particular discussion, we are not going to see, or we are not going to discuss the importance of this methylene, right? In this in the structure, right? Now followed by the nitrogen of this PABA, as I said, para-amino. So we are done with amino. Now para means definitely the amino is found to be a part which has been placed at para position of a phenyl. So phenyl is somewhat like this, right? And to that para-amino, definitely, as I said, para-amino benzoic acid. So we are done with para-amino as well as benzene. Now this is found to be the acidic part. And we have to insert one more thing, as I said, pteridine, derivatized PABA, at the same time glutamic acid, fine? Now to this carboxylic, to this carbonyl, and this carbonyl is found to be the part and parcel of PABA, right? The native PABA. Now to this carbonyl, we need to form one amide linkage. And that is being formed when this glutamic acid is contributing, or rather providing the amino group, right? Fine. Let us assume that this is found to be the alpha amino group of glutamic acid, fine? So alpha amino means this is found to be the alpha carbon, right? To that carbon, definitely you will find the C terminal, right? Fine. Followed by 2-methylene. So that is why I am going to write like this. And finally, we have another carboxylic group. Why? Because glutamic acid is an example of an acidic amino acid. So that is why we have 2 carboxylic group in it, right? So now this is found to be the raw structure of methotrexate, right? Now only thing is that we need to put few functional groups so that we can just complete the structure of methotrexate. So what are the few things that need to be incorporated? 2 amino group. These are the locations where you are supposed to put what? The amino group, right? Fine. And as I said, derivatized PABA, so derivatization at this location, right? Fine. So this is the N terminal which has been derivatized both with the methylene at the same time methyl. The C terminal already being clubbed with the N terminal of what? Glutamic acid, fine. So now this is found to be the structure of methotrexate. So we have a pteridine, of course, it's diamino pteridine. To that pteridine, one methyl is there. We have another methyl amino followed by a phenyl, then carbonyl. It came from benzoic acid, the carboxylic group of benzoic acid. And to this carboxylic group, as it has provided the carbonyl group, this carbonyl group formed an amide linkage with what? The NH of what? NH of glutamic acid. So this is your glutamic acid. So now, this is found to be the overall structure of methotrexate. Now let's see that what are the how we can create the IUPAC name of methotrexate, right? So now for that we need to just let me just rub it off on you. Okay. So if we just create the chemical name, simply it's a gamma glutamyl, then gamma glutamyl, then followed by a benzoyl, then followed by N-methyl amino, or we can say methyl amino, then this is pteridine, fine. But we are not going after creating the chemical name, rather we can just create what the IUPAC name. And for that very reason, first and foremost, we need to fix what the parent moiety. So as we have a carboxylic, we have two carboxylic group, and they are found to be the part and parcel of this glutamic acid. So what we can say, the glutamic acid comprises of how many carbon? So 1, 2, 3, 4, 5, right? So this is about this glutamic acid. So it is basically comprises of what? 5 carbon atoms. So can we call it as a pentadioic acid? Yes, definitely it's a pentadioic acid. To that pentadioic acid, dioic acid, we have an amino followed by a carbonyl, right? Followed, or to be more precise, this is benzoyl, right? Now let us do one thing. Let us just identify the fragments, right? Because after all, it is the proper assembly of various fragments that lead to the formation of what? That lead to the formation of the overall naming of a compound, right? So it will be better to just isolate the fragments so that things will become much easier for us to understand, right? So this is your glutamic acid, but in IUPAC version you are not supposed to call it as glutamic acid. Rather you have to deal with oic acid. So how many oic groups are there? That means 2 carboxylic groups are there. So that means this can be called as 1, 2, 3, 4, 5. That means pentadioic acid. To that pentadioic acid we have an amino, right? We have an amino. Now this amino is linked with what? Another benzoyl, right? To that benzoyl we have a methyl amino, right? This methyl amino is connected to a methyl group, right? And now we have amino groups. So if we just try to put the number or the locate number, it goes like this, right? 5, 6, 7 and 8. So thus we have 2 amino group. They are found to be the part and parcel of, they are associated with pteridine. What are the locations? The locations are position 2 as well as 4. So we have 2, 4, pteridine, and this is 6-yle, because earlier we have not considered pteridine as a parent one, because the parent has been kept here, right? So that is why this should act as a substituent. So hence we can call it as pteridine, and then 6-yle because it's a substituent, right? 6-yle. This 6-yle is connected to a methyl. This methyl is connected to a methyl amino. This methyl amino is connected to a benzoyl. This benzoyl is connected to an amino. And then this amino is found to be a part and parcel of what? Pentadioic acid. So this is how the nomenclature stands, okay? If you have understood the Facton file, or rather if you are in a position to recognize them in a proper way, definitely you can create that one, right? And I strongly refer, please do refer PubChem for this IUPAC learning and all, right? Because first you just try with yourself, then just consult with PubMed or PubChem, right? PubChem, right? And from PubChem only you can get to know about the IUPAC name. So better to recognize each and every fragments. Now just try to find a way by which you can assemble them in a proper way, and finally, and thus you can create what? The entire IUPAC of methotrexate. Okay. So now we are done with almost IUPAC name of methotrexate, right? Now let's straightway deal with the pharmacological things of methotrexate, right? So pharmacology says that it belongs to the pharmacological category of anti-cancer drugs, right? There are several types or forms of cancer which can be treated, or where methotrexate can be a drug of choice, right? Here, like your, we have a lymphoblastic leukemia, right? Leukemia, okay, is found to be one form of cancer, right? In blood cancer, right? In which methotrexate can be a drug of choice, right? And apart from its use in cancer treatment, right, this can be used in the treatment of rheumatoid arthritis, right? So RA, that is rheumatoid arthritis, can also be treated with methotrexate. So this is about the pharmacological category in which methotrexate belongs. Now we can spend few moments with the mechanism by which it is exerting its action and all, right? Or anti-cancer effect and all, right? So now let's do one thing. So how it acts actually. So as I said, methotrexate is sharing a common features with what? With the folic acid, right? It's so, if we just, explain it in a layman's language, what we can say, or in a single sentence, right? Because how it stands actually. So we know that there is a conversion process that should take place, okay, inside a cell. That is the conversion of DHF to THF, right? THF. This is found to be the conversion that is required, right? That is required for what? That is required for the for the making of what? For the making of the raw material, which are used to make DNA. To be more precise, a functional DNA. I mean to say the nitrogenous bases, right? They are being produced, okay, under the proper utilization of what? Folic acid. So folic acid it plays a crucial role, right? And it is the folic acid that need to transform itself, okay? So there are several forms of folic acids, right? All are not found to be important, but they need to or they must be formed, right? They must be formed, otherwise you won't find THF, right? If DHF will not get produced, THF will not come, right? So that is why each and every intermediate they are having their unique role to play, right? But we should concentrate the final form, that is your THF, right? Now DHF means dihydrofolic acid, THF means tetrahydrofolic acid, right? And this conversion is required, and this conversion should take place in presence of what? In presence of an enzyme called DHFR. That is dihydrofolate reductase, right? So it is upon reduction. It is upon reduction means what? Reduction means addition of hydrogen. So here it is dihydro, here it is tetrahydro. That means 2 more hydrogen has been added. So that is why it is the enzyme called DHFR, that is dihydrofolate reductase, right? That is getting inhibited under the influence of methotrexate. This is found to be the single sentence, or if I just want to explain the mechanism in a single sentence, this is how it stands, what we can say, right? So it is the methotrexate that is basically affecting what, or inhibiting what? DHFR, right? And thus it prevents the conversion of what? DHF to THF, okay? And if there is an increased level of DHF, what will happen? It in turn causes a feedback inhibition, okay? A feedback inhibition for the production of feedback inhibition of what? Inhibition of thymidylate synthetase, right? Thymidylate synthetase is the one, okay, that is basically responsible for the production of thymidine, one of the key pyrimidine base with which a functional DNA is getting formed, right? So, once the DHFR is getting inhibited, what will happen? This conversion is getting stopped, right? And now, if there is an excess amount of DHF, what will happen? It in turn increases. It in turn causes what? A feedback inhibition, right? A feedback inhibition that eventually leads to what? The inhibition of thymidylate synthetase. Thus, conversion of uracil to thymidine will get stopped, right? So this is how what will happen. A significant changes occur, right? A significant changes take place, what we can say, and it is the significant changes that causes what? Mutation, because it basically restrain or restrict the process to form what? A functional DNA. And thus, if functional DNA is not getting formed, what will happen? The mutation will take place, right? And it is the mutation that causes what? That causes the malformation of cancerous cells. And that is our intention, right? So with that, we are done with what? The mechanism by which methotrexate is exerting its action. Now, okay. Now let's see the synthesis, right? By which, or the process by which methotrexate is getting formed, right? So here, deliberately, I have just omitted the rest of the part, because we all know that the rest part, who all are there? The PABA, the derivatized PABA, at the same time the glutamic acid, right? So initially, what we'll do, that is, and this is the methylene that need to be connected to an amino, to be more precise, a tertiary amino, right? So now let's do one thing, that this amino should release what? Hydrogen, right? So what is expected? The CH2 should release what? An electronegative atom, because after all, it is a proper mixing of an electronegative as well as positive, right? Things will get clubbed, or things will get ligated, right? So here, as the methylene need to need to form a covalent bond with the nitrogen, so that is why this methylene should have in it a halogen, precisely an halogen, and the nitrogen should release one hydrogen. So it is the dehydrohalogenation that eventually leads to the production of what? A covalent bond between CH2 and N, which is required, right? So now let's do one thing. Let us just prepare this pteridine moiety in an in situ way. That means we'll start from an open system, a partially open system, and we'll think that how this open system can be closed or cyclized, right? And for that very purpose, what can be done is, let's do one thing. If I want to build this, this fused system, the pteridine system, right? How this can be built? Let's do one thing. Let us just isolate this portion from this pteridine moiety, right? If I just isolate this one, what will happen? We are getting, now we have got two different fragments, right? Okay, this is the fragment which should, while taking part in a reaction, they must provide what? The hydrogen, right? So that is why what I have written here, amino, 2 amino, right? Chalo, fine. This 2 amino. And they are found to be the part and parcel of what? This pyrimidine. So it is the pyrimidine that is having what? 2, 4, 5, 6 tetraamino-pyrimidine. Fine. That is found to be one of the starting material. Now this 2 nitrogen need to be connected to 2 different carbon, right? So let's do one thing. Let us put carbon here. Why? Because this is the fragment in which 3 carbon should be there, right? Now this 2 are the carbon, right? That need to be, now we have to think that how this 2 carbon can be connected to this 2 nitrogen, right? How they can be connected, fine. Now for that very purpose, what can be done is, this 2 carbon should be attached to, or should be attached to what? An electronegative atom, because the same thing here also, as this end is providing hydrogen, so we have to search for what? A proper electronegative atom. It can be an oxygen, it can be even a halogen as well, right? So let's do one thing. Let us put here halogen, right? Like your bromine. Fine. So now let's just fulfill the valency here. So we have a CH here, and beneath this we have a C double bond O, right? So with that we got what? The other. We have completed what? The other second reagent, right? The second reagent, fine. Now since this CH2 need to be merged, or need to be connected to a nitrogen, so that is why the CH2 also should be connected to another bromine, right? So thus we have created what? The second reagent. The second reagent is nothing but, it comprises of how many carbon? 3 carbon. 3 carbon means pro. And since it's an aldehyde, so this is propionaldehyde, and this propionaldehyde at its second as well as third position holding what? 2 bromine. So thus we can just create a name for this is 2,3-dibromo propionaldehyde. Propionaldehyde, right? Chalo. So we got 2 essential reagents with which we can initiate the process. So the process should initiate with this tetraamino-pyrimidine and 2,3-dibromo-propionaldehyde. We have already justified that why this 2 bromines should be there, right, at their respective places. What is the role that should be played by this oxygen, okay, while being kept over here, right? Okay. Now let's do one thing. Let us just clean it up and let us see that how the first reaction or the step 1, okay, can be carried out, right? Okay, so here we go with the step 1, right? So as I said, okay, these 2 are the reagents, right? The first one is the tetraamino-pyrimidine. The second one is what? The dihalogenated propionaldehyde. So what will happen? What is expected here? Will go off, right? Go off, right? So what is that product that is getting formed here? Okay, let's see that what is that product that is getting formed here, right? Chalo. So this is found to be the intermediate 1, right? This is the first intermediate that is getting formed, right? Now, what is left in the process? We have to bring what? We can bring PABA, and then subsequently we can bring glutamic acid, or straightway we can bring what? Glutamyl benzamide can also be brought straightway, right? So let's see. So this is the CH2 that needs CH2Br that need to interact with what? The immediate neighbor, that is methylated amino of PABA, right? Chalo. So now how it looks? It looks like this. So after that we have a C double bond O, then we have the alpha amino of glutamic acid. Now to that alpha carbon we have a COH, then followed by CH2, we have 2-methylene, and finally we have a carboxylic group, right? Chalo, fine. So this is the fragment that need to interact with this, right? So better to write here. So this is N-methyl. So this N-methyl, how it can participate in this reaction? The nitrogen should have another hydrogen, because this is secondary amine group, right? So that is why this hydrogen should be there. And if the reaction is on, the action has to happen, then it should happen in this way, right? So on release of HBr, what will happen? The clubbing will take place. The covalent bond will get formed. So what could be the name which can be given to this compound? So this is the portion which is attributed to, okay, I just missed out this one. Fine. This is attributed to what? Glutamyl. So this is basically glutamyl, fine. So this is glutamyl and this is phenyl with CONH2. Can it be called as benzamide? So can we call it as N-methyl amino glutamyl benzamide? So it can be called as like this, EFGHIJKLM. So better to start with glutamyl, fine. So this is glutamyl, then N-methyl amino benzamide. So this is found to be the the third reagent that need to be brought here, right? So with this two, the reaction will occur, right? And what will happen in this process? The HBr will go off. So at the expense of one molecule of HBr, so what will happen? The clubbing will take place, right? We have not yet completed, because apparently it seems that we are done with each and everything, right? But here we stuck, right? We are left with one more step, right? Where one hydrogen need to be eliminated, right? So here it is CH. I forgot to put the hydrogen here, because otherwise the carbon will not get properly, complied with its valency. So here is CH. So what has happened? What we observed in case of methotrexate, it was an aromatic compound, right? So as this pi bond is missing over here, so what need to be done here? The hydrogen need to be eliminated. So if the process involves elimination of hydrogen, it is called as what? Oxidation. So here simply air oxidation will eventually release what? Or remove what? The hydrogen, and thus there is a formation of a pi bond. So what the next step says, that you have to perform air oxidation. Air oxidation, right? It is the air oxidation through which we can eliminate what? This two hydrogen, and thus there is a formation of what? A pi bond. Thus we are done with what? The making of methotrexate. So this is how the synthesis stands, right? Okay. So now let's see that how it overall stands, right? Overall how it stands. So initially, as I said, it is the 2,4,5,6 tetraamino-pteridine. So 2,4,5,6 tetraamino. It's not pteridine, rather it's pyrimidine. Okay, it's pyrimidine. Pteridine we are going to make, right, later on. So now, and the second one is 2,3-dibromo. So 2,3-dibromo, propionaldehyde, because it comprises of 3 carbon, right? So once the condensation occurs, what will happen? There is a formation of pteridine nucleus. So we have a bromomethylated pteridine, what we can say. It's the bromomethylated amino. So if I just want to put the number here, so this is 1, 2, 3, 4, 5, 6, right? So here this is the location where we have 2 hydrogens. So thus the name can be framed like 2,4-diamino, then 5,6 dihydro, then 6 bromomethyl pteridine, right? Okay. So this we have considered as intermediate one. It is the intermediate one, I mean to say this structure, right? It has to interact with what? This glutamyl derivatized PABA. So how this can be named? This is N-methyl, because this is the secondary amine. N-methyl glutamyl. So this is the portion which is glutamyl, right? So glutamyl, as I have written here, glutamyl, followed by para-amino. Para-amino means this is the location where amino group is there, right? So this is para-amino, because we are done with N-methyl, but we have not yet done with amino. So this is para-amino. Para to the benzamide. So this is phenyl with CONH, that is benzamide. So this is the third reagent that need to be incorporated, and it has to be mixed with what? The intermediate one, right? And once the mixing occurred in a proper way, then we are going to get what? A semi-formed methotrexate that we are going to see. So as you see, this is another intermediate that is getting formed, right? So why I am calling it as a semi, or semi methotrexate, because almost it is having, if I just want to superimpose the structure of methotrexate, right, all will get superimposed, right? You can find 99% homology, but only, it differs from the original one. How? With respect to this area, right? Because this is the area which is still in hydrogenated state, right? This hydrogenation need to be dehydrogenated, and thus we can create another pi bond here, right? So it is through air oxidation what happened. This two other hydrogen, okay, here one hydrogen is there, fine. So this two other hydrogen that is getting eliminated, and thus there is a formation of what? This pi bond, right? So this is the final form. This is the final form. Now, if I want to superimpose methotrexate on it, definitely things will get properly superimposed, right? You won't find not even a 0.1% difference, right? So this is how the entire synthesis stands, right? Okay, because there is a space constraint, no? So that is why it has been shown in two different parts, what we can say, right? So anyway, thank you. So this is, I hope you have understood that the fact and file. So it's simply a demonstration, right? Only thing is the what I can suggest you, right? Just understand the fact and file and put it in pen and paper, because chemistry without pen and paper is incomplete, absolutely incomplete, right? Anyway, so thanks for being with us, right? Definitely in future we'll bring so many things, right? Okay, just keep boosting me, boosting me so that I can grow along with you. Okay, thank you. We'll meet soon. Thank you.